Hi, my name is Fabio Niephaus. I'm a PhD student and member of the Software Architecture Group at Hasso-Plattner Institute in Potsdam, Germany. Today I'd like to present our Onward paper on example-based live programming for everyone, building language-agnostic tools for live programming with the language server protocol and GraalVM. This is work I've done together with my colleagues Patrick, Rein and Robert Hirschfeld, as well as some of our recent master students. Live programming is a form of interactive exploratory programming. It helps developers to better understand the dynamic behavior of the programs that they build. Instead of having to think about the code in your head, the programming environment can show you the information that you're looking for. Live programming can provide very short feedback loops, for instance by allowing developers to modify applications at runtime. As part of our work, we looked at a special form of live programming, namely example-based live programming systems. These systems allow developers to annotate code with examples to generate live feedback. One such system that we've built is Babylonian.js. It's integrated into Lively 4, a Lively kernel programming environment. And here's a screenshot of the editor. It shows you some JavaScript code annotated with examples and so-called probes. We get to this in a minute. Here's another screenshot of a different system. This is Babylonian S, which we are currently working on, and it's integrated into a Squeak Smalltalk programming environment. And of course, there are many other ELP systems that we have also mentioned in our paper. So let's get to our motivation. ELP systems require program instrumentation, for instance to record intermediate results of a program. However, there are very different approaches to program instrumentation. One could use code rewriting or the runtime environment to gather runtime information. ELP systems are therefore usually tied to a specific language ecosystem, because you either rely on something specific to the language or the runtime environment. Having to implement ELP tooling from scratch therefore is very expensive, and it makes it very hard to reach a broad user base. So the research question that we asked ourselves was, can live programming systems be built in such a way that they are independent from both the language and the programming environment? To give you some background, let me introduce you to GraalVM, a high-performance polyglot virtual machine. It comes with Truffle, a language implementation framework. In this framework, all languages supported by GraalVM are implemented. Moreover, Truffle has a dedicated API for program instrumentation. What's interesting about this API is that it allows the language-agnostic implementation of tools such as debuggers and profilers. Why is that interesting? Well, because the tools are only implemented once, and whenever someone implements another language in Truffle, you get all these tools for free. So that saves a lot of work. Let's talk about another interesting technology, the language server protocol. It decouples a language from a specific programming environment and supports common features such as auto-completion or go-to definition. It is a classic example for a client-server-based system. The developer interacts with a programming environment. This programming environment is connected to a language server for a specific language. When the developer, for instance, triggers autocompletion, the LSP client of the programming environment can request suggestions for autocompletion from the language server. The language server then reads your program and performs static or dynamic analysis or both and responds to the programming environment. And that way, we can decouple a programming environment from a specific language. Last year, we worked on the GraalVM language server, which is an implementation of a language server in Truffle. So it is language agnostic, very similar to the debugging and profiling tools that GraalVM already provides. So every language implemented in Truffle gets a language server almost for free. That means now we have an architecture that is independent from the programming environment as well as from the programming language. We presented a paper on this last year at the Dynamic Language Symposium if you want to learn more. To come back to our research question, Can live programming systems be built in such a way that they are independent from both the language and the programming environment? If we look at the different ELP components, it looks quite similar to what I've shown you before. A developer interacts with the programming environment, which modifies a program. The program runs on a runtime environment, and the runtime environment can report dynamic runtime information back to the programming environment. If we use the LSP in our GraalVM language server, we can build an ELP system that is independent from a language and independent from a programming environment. In fact, one key contribution we make in our paper is how we build a live feedback loop on top of the language server protocol. Now let me show you a demo of our system. This is Visual Studio Code running our extension for example-based live programming. In the background, it communicates through the LSP with our GraalVM language server. Note that this is the latest version of our extension with a couple of new features that I now like to show you in action. Let's start with defining an example. We call the example 10 and we set n to 10. We can now see that the return value is undefined because the function doesn't return anything yet. I can also see that by adding a probe. So let's start implementing the algorithm. We set x to 0 and y to 1 and we return x. Now we can see that this function returns 0 for our given example. Of course, the 10th number in the Fibonacci sequence is not 0, it's 55. We can assert that by turning our probe into an assertion. Now the assertion is failing because we haven't fully implemented the algorithm yet. So let's do that. We repeat n times. We set z to x. We set x to y. And we set y to z plus y. Now the algorithm is complete, the assertion is true, and we can see the return value on the top. I can also add another example. Let's call it 20 and set n to 20. And we can see the return value for that as well. You also notice that we are encoding example names with emojis. So this rocket corresponds to this rocket and corresponds to our example with the name 10. While this other example 20 returns 6765, which is not 55, which is why the assertion is no longer true. Of course, we can make this assertion example specific and now it's true again. Another thing that we can do is select code and turn it into a probe as well. Now I've only selected Z, so we can see all values for Z for each iteration and for each example. I can move my mouse even further and now the expression is invalid, which we can see, and I can turn it into a valid expression again, and now we basically get to see the Y values. Moreover, I can click on this little bug, which will put me into a debugger session for the corresponding example, and now I can step through the code. Lastly, this tool also works for other languages as well. So here you can see the same implementation in Ruby, and the tool works in exactly the same way. As I mentioned earlier, live programming helps developers to better understand the dynamic behavior of their programs. Polyglot programming, on the other hand, is the practice of writing code in multiple languages throughout the same software project. Traditional approaches to polyglot programming, for instance based on foreign function interfaces or inter-process communication, often rely on the operating system or a network connection. These approaches usually introduce boundaries for tools, so that means if you are in a debugger, you can't step through an FFI call, or you can't step through an IPC call, for instance. So you can't see what's behind a language boundary. GraalVM provides a language-level approach to polyglot programming, which means that languages can directly exchange objects and send messages between each other. Since our approach is language-agnostic, we can use our ELP tooling for building polyglot applications. This helps developers to not only better understand the dynamic behavior of their programs, but also the interaction between code written in different languages. Let me show you a demo. We are back in the Visual Studio Code instance from the previous demo. Now we see a plot function written in R, which consumes another function and plots that function from 0 to 20 using the lattice library. This function returns an SVG, and now I'd like to use it to plot the Fibonacci function that we've written in the previous demo. For that, we first need to export the original Fibonacci function using GraalVM's Polyglot API. What we can see is that our example-based live programming system is still active, the examples are still working, and here's a probe, and this probe is not reached because the code on the top doesn't call into the R code. On the other side, what we need to do is we need to use the Polyglot API to evaluate the JavaScript file from the top. And now we can import the function using import Fibonacci, import being the counterpart to Polyglot export. Finally, we define an example for this function. Let's call it fib, and we set func to import Fibonacci. This library takes some time for rendering the SVG, but we get immediate feedback and this probe is active, and we can see the Fibonacci series here. What we can also see is that the return value for the example is an XML, more specifically an SVG. Our system has detected that and renders the graphic in here. So this is the plot. We can actually see the plot in this hover. And lastly, we can again click on the little bug. It will take some time, but eventually we will enter a debugger session. And now that we are in this debugger session, we can step through the functions. Now we are in lapply, but now I can also do something that you usually can't do with other approaches to polyglot programming. I can step right into JavaScript from R. You can even see that here on the call stack panel. This is JavaScript and this is R. So I'm actually stepping through different languages at the same time, fully integrated with our tooling. To conclude our talk, example-based live programming can be provided in a language-agnostic and environment-agnostic way. And we were able to demonstrate that using GraalVM, the language server protocol, and Visual Studio Code. Furthermore, our ELP system can also be used for polyglot programming. In the future, we'd like to extend and improve our current implementation, for example, with better UI components that provide more interactivity. Also, we want to add support for other programming environments. Moreover, it would be interesting to explore how our approach could be applied to static languages or languages that are not file-based, such as Smalltalk. And lastly, it would be great to extend the official LSP specification with ELP capabilities. If you find this work interesting, have a look at our paper, and if you'd like to give our ELP system a try, you can find the code on GitHub and our VS Code extension on the Visual Studio Marketplace. And with that, I'm happy to take your questions. Thanks!